So welcome everybody. It's a big pleasure to have Olivier Witasse today here. He will give us a talk about solar system exploration with the European Space Agency missions. He has actually studied fundamental physics at Paris Sud, ENS, and University Claude Bernard. So he came more and more close to Grenoble, where he did then his PhD on the ionospheres of Earth and Mars at the University Joseph Fauré. And then he went directly as a postdoc to ESA, and there he stayed for 2 years. He did a little excursion to the Belgium observatory, but this was only 4 months, and then he came back to ESA, where he got project scientists for solar system missions. He did a set of missions, so he was permanent. What he's doing now since 21 years, so he was involved in the missions of Huygens, Venus Express, Mars Express, several missions, and icy moons and giant gas explorers. And yeah, today he will give us an overview of what is going on presently and in future at ESA. Thank you very much. And please, for those participants who are online, you can put your questions in the Q&A during the talk, and we will read them to the speaker after the presentation. The stage is yours.
Good. Thank you, Angelica, and thank you for the invitation. I'm back to Grenoble, so I did my PhD indeed more than 20 years ago. So I spent a few years in Grenoble, but I never had the opportunity to visit ESRF. So that's done now. So thank you for the invitation. It's always a pleasure to discuss our project and our planetary missions. And in this talk, because it's a kind of collaboration with ASRF, I decided to show a little bit of overview of our missions. So planetary and heliophysics, a little bit of a selection of questions, outstanding questions that we would like to solve with our mission, so in planetary science and heliophysics. Also a selection of very interesting planetary science results over the last few years. Because I am the main responsible for the JUICE mission, so the Jupiter Icy Moon mission, I decided to talk a little bit more about this one. And then a few areas of collaboration with Seacroft facilities, because also it's the goal of my visit to discuss with Angelica and colleagues to see how we could work more together in the future. So that's the plan for today. So just in short, what are our missions? So at the European Space Agency, there are many directorates. I'm working for the Directorate of Science. So we built missions for the scientific communities. There is the astrophysics part, but I am more on the planetary science and heliophysics. So this is an overview of all our missions, so per planet. So the bottom line here, it's all the missions that have stopped working. But there is a lot of data into the archive. So there was the Ulysses missions to study the sun. The Venus Express at Venus. Giotto was our first planetary mission to explore, to fly by the Halley comet. Then there were a few missions for the Earth's magnetosphere, the moon, the famous Rosetta mission to visit the comet, and the Cassini-Huygens mission, which stopped working in 2017. So all those missions, we call that legacy. So there is non-activation, but there are still many people working still on the data set. Then this line is the mission we are operating. So here they are at full speed. We do the science planning, we do the archive, and the scientific community is heavily involved in those. So starting from the sun, we have the solar orbiter mission, many missions for the sun, sometimes in collaboration. For example, I know the IRIS, they are in collaboration, and SOHO as well with NASA. BepiColombo is en route to Mercury. So that's a very interesting mission. So it was launched in 2018, and in 2 years it will reach Mercury. So in 2 years there will be a lot of new images, new data from Mercury. It will be very interesting. We have still a long-standing mission around the Earth for the Earth's magnetosphere, which is called Cluster, more than 20 years in space. It's interesting because those missions usually they are built to last 1 or 2 years by design, because we think that's the baseline mission, but then they are still active for more than 20 years. It's the same for Mars Express, around Mars since 2003. Still working, again, designed for 2 years. But since it's working well, we continue operating this mission. We have another orbiter around Mars, which is called ExoMars. And then we have the JUICE mission, which was launched last year, but I will talk about that later. And then we have a few missions under preparation. So Proba 3, it's a mission for the Sun. Envision just selected a mission to Venus. SMILE, it's a magnetospheric mission for in collaboration with JANA. Another Comet mission, the ExoMars rover, which hopefully will launch before the end of the decade. This mission was not easy. It's not an easy one, but we continue it. And there is also a very interesting mission with the Japanese colleagues to bring back samples from one of the Martian moon, which is called Phobos. So you see, all in all, we touch most of the planet in the solar system, except the most outer one, which are difficult to reach. But we are very active in all those missions. So why do we want to explore the solar system? There are many open questions. I have selected a few ones. Maybe I could start with the formation and evolution of the solar system. It's always a big question. When we explore the solar system now, we see the picture as it is now. But how was it in the past? And we know that the solar system evolved with time. So what we see now is not the same picture as has happened 3, 4, 5 billion years ago. And that's quite interesting to study. In particular, we know that the planets, they were not exactly at the same time as they are now. There is the migration of the planet. Also, the Earth was not the same 4 billion years ago. Venus was not the same. Mars was not the same, etc. and etc. And it's very important if we want to understand our solar system, to understand how it is now, how it was in the past, how it evolved, and how it will evolve in the future. And one of the big questions is also about life, because we want to understand the evolution of the solar system, allow to life to start on the Earth. But could we have life somewhere else? That's a big question. The somewhere else could be Mars. There have been many missions to Mars to find signs of life. And the ExoMars rover has the goal to find some sign of past life on the surface, if it exists. But before looking for life, we need also to find the ingredient for life. And one of the main ingredients is liquid water. So the other question is, where is the liquid water? Again, we wanted to go to Mars because Mars is the most interesting target for find life and maybe for liquid water. We did not find very big evidence of liquid water, but I will talk about that a bit later. What we find is that there was liquid water on the surface in the old history of Mars. That's very interesting. There was a global ocean at the surface of Mars. So life could have started on Mars, but at the moment there is no liquid water. The big surprise came 20 years ago when we find liquid water inside the moons of giant planets. So in fact, Mars, we didn't find any liquid water, but the most interesting target are the moons around Jupiter, Saturn, and that's why we send many missions there. Liquid water is important, but in addition to liquid water, do we have other ingredients for life, and that we call the search for habitable place. And it's one of the goals of our missions to Jupiter is whether around a planet like Jupiter, there are places that could be a habitat for life. And we would like to explore the icy moons of Jupiter, in particular Europa and Ganymede, because we think there are good places to host a habitat. But that's a question mark. Linked to habitability, we want to know also more about the interior structure of planet and moon. I mean, we know how difficult it is to understand the own interior structure of the Earth, but we would like to do the same for the other planet and the moon, because if you understand how the planets are inside, you can understand also their habitability. And last but not least, I mentioned also Uranus and Neptune. They are the two big planets that still are lacking a lot of exploration because they are very far away. We got only the two flybys from the Voyager 2 spacecraft long time ago, but we really need a further exploration of these two planets to complete the full picture of the solar system. So you see many questions. So it's quite fascinating to work in that field, and that's why we prepare so many missions. In terms of heliophysics, it's less my field, but I thought I will discuss a few topics as well. So heliophysics, that's the study of the heliosphere. So basically all the solar system and to understand the interaction between the sun and the planet, in particular our own planet. And there are many open questions like the origin of the solar wind, all the eruptive events like a coronal mass ejection, solar flares, how to understand the solar cycle of 11 years and the dynamo, how the magnetic field is generated inside the sun. The corona around the sun, which is 1 million degrees, very, very hot compared to the surface of the sun. We don't understand this change of temperature. How the particle propagates from the sun into the heliospheres and also the galactic cosmic rays, which come from outside the heliosphere that go into our solar system. And also a new field, which is dust plasma interaction, because in the heliosphere, there is a lot of plasma with the solar wind, but there are also dust particles. And now we start to study how those two components, they interact with each other. It's an emerging field. So also a very rich field of physics. And heliophysics, also there is a big focus on our Earth. So all the coupling between what is happening 80 kilometers above our head. So where you have the aurora, the ionosphere, the neutral part of the atmosphere, which is called the thermosphere, and all this coupling between all these layers and also the magnetosphere. And that's also very important because it's our own planet, and we want to understand how how the sun influences our planet. And it's important because everything which is happening there, in fact, contribute to the shielding of the solar input. So we are happy to be shielded from the solar influence. And there is another application which is called space weather, because the sun influences our planet, our atmosphere, and sometimes it can be disturbing. So for example, in terms of radiation, when we travel by plane, but also for the astronaut. So they can be in danger when they are in space if there is a solar event. Our satellite can suffer from solar disturbances. There can be also some disturbance in the radio communication and in the power system also if there is a big solar storm, and that can affect also the navigation capability of with the GPS satellite. So it's not only important to understand what is happening in terms of physics in the upper atmosphere, but also there is also an impact on our on the daily life, but our life in general. So that's the kind of open question that we have in planetary science. And now I wanted to select a few results from planetary missions, which I think are very, very interesting. First is it's about Venus. There have been a few missions to Venus. Venus is very interesting because that's the closest planet to the Earth. It looks like the Earth in terms of mass, size. So it's a twin planet. But of course, they are very different. We know the conditions at Venus are completely different than on Earth. There is a huge greenhouse effect. And one of the questions is why two similar planets in size, mass, and also location in the solar system are very different in terms of environment. And one question that we have, because we know from radar images from previous missions from NASA, we know there are a lot of volcanoes on Venus. So all these features that you see here from radar images and all of these are volcanoes and lava flows. So we know that 500 million years ago, somehow, there was a huge resurfacing of Venus. So all the volcanoes were active and all the lava flows covered all the surface. So in fact, we cannot go back in time beyond 500 million years ago. We can only see the history of Venus only recently. It's not like the moon, the Mars. We can draw the history over the full solar system history, but not at Venus. So that's something very peculiar. So there was a lot of volcanic activities. And the question is, or was, do we still have active volcanoes on Venus? And the problem is that when we observe Venus, we have the clouds here all the time, so we cannot see the surface. So it's not possible to answer this question very easily with telescopes and so on. So we need to send special satellite with special instrumentation that can go through the cloud and try to see something. So the question is, do we have active volcanoes on Venus? And we launched a mission which was called Venus Express 15 years ago. And we got a few evidence that indeed there are active volcanoes on Venus. That was, I think it's not well advertised because I think it's a very important result. Of course, there is not a clear identification because we are not on the surface of Venus and we cannot see an erupting volcano. That would be the final proof. But with this mission, we got a few information, such as, for example, the amount of SO2 in the atmosphere that we measured with Venus Express. So that's from a previous mission. So that's the level of SO2 in the atmosphere. And there was a peak here during the mission. And SO2, it's a volcanic gas. So it's compatible with a volcanic eruption, which release some SO2 gas in the atmosphere. And then we see the decay. So that's one piece of information, but one is not enough. Because the next extraordinary claim, you need a lot of evidence. That's how we work with data. Then we use some infrared images, and here it's a volcanic dome on the surface. So with the infrared light, you can go through the clouds, and you can get an image, not super detailed because of the cloud structure, which is very dense, but still you can get something like that. So the colors means different infrared levels and what we call emissivity. So the different colors mean there is different properties of the surface. And on the top of the dome, of this volcanic dome, the properties of the surface is really different. And it was interpreted as a young surface. Young means a few million years ago. Huh? So that young, it's also, we need to see the geological time scale. But that's compatible with the volcanic activities a few billion years ago, which means like yesterday. That's another piece of evidence. And then here from another instrument, which was an infrared camera, we find also, so that's why the colors are a bit special because it's infrared. We find also, looking at the data at different moments, we find some different behavior, different properties in terms of temperature. So for example, hotspot here and here, which is also compatible with recent volcanic activities. So that was quite interesting. And it was confirmed with another mission. So that was released less than 2 years ago, because there was a NASA mission 20 or 25 years ago. It was radar images. So here you see radar images. And people look back at the data. That's why it's good to have a good archive, and you can even do science of the data which are 50 years old. And they looked at some of the volcanic edifices here on the surface of Venus at 2 different moments in time. And they find some differences between this image and this image. This is a radar image, so not very detailed in terms of spatial resolution, but this is what we have when we have radar images. And if you look at the 2 surface features here and here, and they find that there are differences in this area. I'm not an expert in radar, but this was published, so the work was properly documented. And they find some differences that they interpreted as a new lava flow. So that's, again, another piece of evidence. So we have different pieces of evidence which tell us that there are some activities on the surface of Venus. So that was for Venus. Another example which we like very much in planetary science is, you may have heard about this Enceladus moon, a very special moon around Saturn. Very, very small, just a few hundred of kilometers of diameter. So we did not expect any activities for this moon, because the smaller the moon, the less activity you have in principle. But with the Cassini mission, which flew there from 2004 to 2017, doing some flybys, they have detected what they call the plumes of Enceladus. That was something, a big surprise. And now everybody would like to go back to Enceladus, propose mission to Enceladus. That's one of the most interesting targets in the solar system, I have to say, because we did not expect that for such a small moon, there will be some activities. So here we see a plume, so it's water vapor and other gases which escape the surface and go into space. And since it's liquid, so here it's an artistic view of the plumes here which escape from the South Pole. And in fact, the water vapor, or the water, comes from the interior of the moon through some cracks in the South Pole, and they originate from the subsurface liquid ocean. So I was talking about the water before because we want to find water in the solar system. So where is the water? But the water, at least part of the water in the solar system is inside moons like Enceladus. So that's quite fascinating. We don't say there is life there. It would be too much of a step. But it's a very interesting target to study the conditions for life. So Enceladus, very, very interesting moon. Then there was a talking stick about liquid water. It's a very important topic. I wanted to make the analog between what we study on Earth and what we can study on other planets. And one interesting analog is the lake, the Vostok Lake in Antarctica, so a few kilometers underneath the ice crust here. So it's being studied. And underneath this crust, a few kilometers in the subsurface, you have this lake, which very interesting properties. So you have also sediment, ice, methane hydrate, etc. So it's a very interesting place to study extreme environment. So that's in Antarctica. Could we have a similar lake on other planet? And maybe it's still being debated, but we have a radar on board the Mars Express mission. And 4 or 5 years ago, they have interpreted data from the South Pole of Mars. So this is the South Pole here. So we have polar caps on the north and in the south hemisphere of Mars. So this is the south one. And in this area, they find very peculiar radar structure. So this is a radar working at a few megahertz. So you penetrate the subsurface, and then the echo that you get back to the spacecraft indicate what is happening underneath the surface. So you see different layers. And here, this bright reflector that you see here were interpreted as a lake, similarly to the Vostok Lake here. So on Earth, it's a few kilometers below the surface. At Mars, here the distance is 1.5 kilometers. So they interpret it as liquid water. So liquid water, it's a big topic. So because it's a big topic, it's being debated a lot. So there is the team which published the data, and there are the other scientific community that think it's wrong. It's a wrong interpretation. So there is a lot of debate. But this is how science progresses in many fields, and in particular in planetary science. People sometimes disagree, and they try to interpret the data in a different way. But at the moment, this is what it is. There is a claim that there is a liquid water 1.5 kilometers in the lake underneath the surface of Mars. I mentioned Enceladus already. We have a similar situation. So you have the icy crust, and here it's not a lake, it's a global ocean. So in studying also this kind of extreme environment at Earth is also very useful to study what is happening in other places, like the Enceladus moon around Saturn, when you have the crust, the ocean, also methane, hydrates, minerals, ice, and so on. So you have similar processes which happen on this moon and on Earth. So it's very, very interesting to study. That was for a short overview of open questions, a selection of results. So now we'll move to the JUICE mission. So this is the mission I'm working on. So we started in 2015, the development, and we launched last year in April. So because it was a very intense moment, I decided to show it again to you and to show it again for me.
Allumage de EAP, décollage.
It was an automatic camera. There are not someone. So very, very emotional when you work for a mission, and then when it goes to space. I mean, it's the most critical moment of a mission, because everything can go wrong in this minute. So, but everything went well, so we were quite happy. So it was on the 14th of April last year. And I got always this question, how do you do to work on planetary missions? You need to be very patient. Yes, because in fact, this is the timeline of the mission. So what you have seen, the launch, which happened in April, it's only the middle of the project. Because we started in 2007 with the call for proposal. So we had a certain amount of money to spend in the mission. We asked the scientific community to send us the ideas. It took 5 years to proceed to select, to have many mission in competition to see which one is the best. Then it took 8 years to develop with the industry and the laboratory which provide all the instruments on board. Then it will take another 8 years to go to Jupiter because it's a big spacecraft and Jupiter is far away. So it takes 8 years. You will see how we do that. And then it will take another 8 years of mission, data analysis, archive. So I started here. Before me, there was another scientist in charge, but the person was about to retire or had to retire at some point. So I was selected to replace this person. And I was selected because I could follow the project until the end. So they were looking for someone born in 72, and I'm born in 72. So that's cool. But in general, we need to be very patient with when we work with the planetary mission because it's easily a work of 30 years, even more. So why do we go there? Why do we go to Jupiter? We will study Jupiter, of course, but the main target will be the moons of Jupiter. And in particular, Europa, Ganymede, and Callisto. I put the fourth one, Io, which is the fourth Galilean moon. But Io is completely different from the other. It's more a magmatic moon with a lot of volcanic activity. So it's fact, Io is the most active body in the solar system. There is a volcanic eruption every day. But in our case, we are mainly interested in those moons. They are called the icy moons because they are covered by ice and there is a lot of ice inside. And what is interesting is, similarly to Enceladus, if we were able to look inside the moon, we will find a lot of liquid water. And liquid water, again, important ingredient for life. And the liquid water, where it is, we know there is liquid water, but we don't know exactly at which depth under the surface. For example, for Ganymede, we don't know if the liquid water here is at 100 kilometers, 150 kilometers. We don't know how big it is. Do we have a layer of 100 kilometers of water? So we think that there is maybe 6 or 7 times more water inside those moons than on Earth. So you look at all the ocean on Earth, you multiply by 7, 8, and this is all the water inside the moons of Jupiter. So Europa, we are pretty sure there is liquid water. Ganymede, we are sure. And Callisto, the last Galilean moon, we don't know. We think there might be a liquid water, but we are not really sure. So with our mission, we are going to study Ganymede in detail, Callisto also, and a little bit Europa. And we will compare the moons to see what's going on. So it's very interesting. But we are not going to look only at the moons. We are going to look at Jupiter, because if you are interested in whether a moon is habitable in the Jupiter system, you need to understand the Jupiter system. So you need to study Jupiter, the magnetic field, the other moons, the dust, and how everything interacts with each other. There is a lot of couplings, gravitational coupling. So the moons are attracted by Jupiter. We have the tides. That's why the moon, they change shape. That's why inside it's heated. That's why you have the ice becoming water. So there is a lot of gravitational interaction. And there is a lot of electromagnetism interaction because of the strong magnetic field of Jupiter. So you have the aurorae on Jupiter. You have particles traveling in the magnetic field tube from the moons to Jupiter, the moon to the moon. It's a very complex system. And one of the illustrations are indeed the aurorae on Jupiter that we can image from the ground in the UV, for example. And the processes of aurora is similar to what is happening on Earth. Not exactly the same, but similar. It's particles, energetic particles, which impact the atmosphere of Jupiter. But in addition, you have this strange spot here and here, which are the aurorae due to the moons of Jupiter. So you imagine a magnetic field line connecting the moon and Jupiter. So it's invisible. But you have particles following the magnetic field because the energetic particles, the charged particles, they like to follow the magnetic field. And they impact the atmosphere of Jupiter and they create an aurorae in a hot spot here. But this is due to one of the moons, for example, Io, Europa, or Ganymede. So you can see here the link between the planet and the moon, and we need to understand those links. And that's the visual illustration of that the planet and the moon, they are linked to each other. So we do planetary science, but because Jupiter with the many moons around the magnetosphere, it's a kind of archetype or model for exoplanet. Because now we also, there is the field of exoplanet, we find maybe 5,000 different systems of exoplanet, and many of them look like Jupiter with a miniaturized solar system. So studying Jupiter and the moon, it's also useful to study exoplanet. So we have also the exoplanet community, which are very interesting with our future result, because of course you cannot go to an exoplanet to study in situ. But studying a planet like Jupiter and the gas giant is very interesting also for exoplanet science. So you see that our field is very, very, very broad. So how do we go there? What did we send? So this is the spacecraft that we've built with the European industry. So I would say it's the standard spacecraft, but it's a big one, six ton. What is special is the shape of the solar panels. We have a very special solar panel, very huge, because we are far from the sun. So we need to have this huge solar panel, which is something like almost 100 square meters. So first time we build this kind of huge solar panel. So we have all the instrument here. So all the remote sensing, the cameras, I will not describe in the detail, but we have 10 instruments in total. We have the radar antenna here to do like for the Lake Vostok to probe the subsurface of the ice. So this is a radar antenna. We have a long boom here, 10 meters, to put all the sensitive instrument to measure the magnetic field and electric field. Because we want to measure the magnetic field of Jupiter and the moon, and we don't want to measure the magnetic field from the spacecraft. Because in the spacecraft, you have a lot of electronics, cables. And if you have a magnetometer, you want to measure the real magnetic field. So you need to be as far as possible from the spacecraft. So we put everything as far as possible here. We have many different antennas for plasma physics. But it's a big spacecraft with a lot of instrumentation. So that's how the spacecraft look like in real. So with the people here, so doing testing here. So you see how a spacecraft look like from this kind of image. And that was one of the final latest image of the spacecraft before it was put on top of the rocket. So in Kourou, so with the escort of the people to make sure that the spacecraft will be well attached to the rocket. So you see that's the big antenna to communicate with the Earth. A smaller one when we cannot point this one to the Earth. So we have still this one to use. That's the solar panels we were stored, and then they were deployed shortly after launch. So it's also an interesting piece of hardware. So now quickly, how we go from Earth to Jupiter and what do we do there? So it's a small animation, and in 4 minutes, we do something like 15 years. So it's a bit accelerated. I don't know why the sound is always too loud. So we launched, so that's the sun, so Mercury, Venus, Earth, Mars, and Jupiter will come later, you will see. So we launch here JUICE from Earth in April. So we start from the Earth. We cannot go directly to Jupiter because the spacecraft is too heavy. And we rely on what we call gravity assist. So we do gravity flybys of Earth, Venus to get more and more energy to be able to go to Jupiter. This is the way we can save fuel on board the spacecraft. So otherwise, we will have a 10-ton spacecraft. It will not be possible to send the spacecraft to Jupiter. So we call that these gravity assist techniques, which work very well. So we need to do a few orbits around the sun. Here, so the first orbit will come back to the Earth. In fact, in August. So this August, if you look at the sky, you will see JUICE passing 20th of August. And the interesting aspect of this one is that we do a flyby of the moon at the same time. That's the first time we'll do a gravity assist of the Earth and the moon at the same time. So it's something, in terms of navigation, it's something new. So we do, let me continue. So we do moon and then Earth. And you see how the trajectory is changed. Huh? So then where are we? So we have done the first of the Earth. Then we go to Venus. Venus is also a big planet, so it's good we can use the gravity field to change the direction and the velocity. So it's good. So we do, so that's in August 25. So then we got a little bit more velocity. We go beyond the Mars orbit. We come back to the Earth. Here we miss the moon, okay? The moon is not always at the right place, but this is what it is. Then we do Earth's gravity assist. Then we missed Mars. That would have been nice to have a flyby of Mars, but Mars was not at the right place. Here we are a little bit in the asteroid belt. We'll make sure we don't collide with an asteroid, but that should be okay. Then we have the final flyby, not far from the moon. And we will say here the final bye-bye to the Earth in January 29. So I'm pretty sure we'll take a picture to say bye-bye. And then we have the necessity, the necessary velocity to reach Jupiter. Jupiter is here. Now we will avoid to collide an asteroid. We arrive at Jupiter, and then we start the mission. So here, there is a very specific aspect. Again, in terms of navigation, it's quite interesting. So if we want to get captured by the gravity field of Jupiter, we need to decelerate the spacecraft. Otherwise, it's only a flyby. So we have not done all this work to have only one flyby and then bye-bye. So we want to stay in the Jupiter system. So here we need to switch on the engine on the right direction, of course, and we decelerate the spacecraft such that it's captured by the gravity field of Jupiter. But to help this process, before going into orbit around Jupiter, we do a flyby of Ganymede that you see here, so the biggest moon of the solar system, which is bigger than Mercury, by the way. So we do a flyby, so a gravity assist at Ganymede, this time not to accelerate, as we do for the Earth and Venus, but this time to decelerate. So if you go on the right side of a planet and moon, or on the right side, you accelerate. If you go on the other side, you decelerate. So we go this time on the right side. We decelerate a little bit with Ganymede, and then we switch on the engine to be captured by Jupiter gravity. So this is what is illustrated here. So we do a close flyby at 400 kilometers. Full autonomy, because we cannot control the spacecraft. I mean, it's too far. And then we are in the Jupiter system, and we can have the flybys. So we will do the flybys of all the moons, so Europa, Ganymede, and Callisto, for 2.5 or 3 years. So we orbit Jupiter, and then from time to time, one every 2 orbits, something like that, we do a flyby of a moon. So here I will show you a few examples. So I think we will go soon to Europa. So here it's an example of a flyby of the Europa moon, so 400 kilometers. So, and doing this kind of flyby, we will operate all the instruments. So all the cameras, the radar, geophysics, and so on. So because the flyby is very short, so everything at the same time, and then we take a few weeks to download the data on the Earth. That's an example of a Callisto flyby. So there will be 2 flybys of Europa, 20 or more of Callisto, and 10 or more of Ganymede. At some point, we'll use the gravity assist of Callisto flyby to incline the orbit, because most of the trajectory is in the equatorial plane of Jupiter, because the moon, they orbit in the equatorial plane of Jupiter. But sometimes we'll incline the orbit to look more at the poles of Jupiter to better have a view of the aurorae, for example. And then we go back to the equatorial plane and we continue our missions. And at the end, that's also a big first, we'll enter into orbit around Ganymede. So first we enter in orbit around Jupiter, and then at the end of the mission, we enter in orbit around Ganymede. So we still need to keep some fuel inside the spacecraft to make these maneuvers. And then we'll go closer and closer to Ganymede, and Ganymede is our main target. We want to know everything. Where is this liquid water? How to understand the surface properties, composition, mineralogy, the magnetic field, because Ganymede is the only moon in the solar system to generate its own magnetic field, so very special moon. And the magnetic field of Ganymede interact with the magnetic field of Jupiter, so it's something completely crazy in terms of plasma physics. And then at the end, there will be no more fuel in the spacecraft, so we cannot control, and the spacecraft will not work at some point. And then we'll impact Ganymede, so it will be a crash on the surface of Ganymede, and that will be the end of the mission. Maybe 2035, 36. We will see once we are there. So that was for the planetary part. So just to conclude, because I have this visit and possible collaboration with ISRF, I wanted to show a few examples of interesting collaboration, what you are doing in RSRF and how is it useful for planetary science. So I selected a few examples. There are many more, of course. So there was a study to understand the upper atmosphere of Titan. Titan is the biggest moon of Saturn. Very interesting also from the astrobiology point of view. And the particularity of this moon is there is a huge or dense atmosphere, in fact, with a pressure higher than on Earth. So it's a very dense atmosphere, and you have a very special, nitrogen and methane mainly. That's the main component of the atmosphere. But when those particles are broken by solar radiation or by particles, then you have a very special chemistry that leads to even a haze around the planet. And there have been some synchrotron studies of analogs of these particles, organic particles in the atmosphere, to understand their behavior and to compare with the data, in particular from in situ data, from Huygens, and from infrared data from Cassini. And with this kind of study, experimental study, they were able to understand really all these different data sets. So it's an example of interesting collaboration between synchrotron facilities and planetary science. Another one is a sample return. So here I selected one example, which is from NASA, that they returned sample last September. You may have heard about it. So that's an example. They visited an asteroid which is called Bennu. So that was their orbit. So they were there between 2018 and 2020, and they were back 2023 with many samples that they have collected during this phase. So they landed on the surface, they took the sample and back to the Earth. So in terms of technology, it's really remarkable. And I know that there will be some analyses in the UK, this diamond light source, and also I understand from ISRF. So the idea is really you bring back samples from something, an asteroid or a planet, and you study with the most powerful techniques like the synchrotron facility to understand their structure, mineralogy, and so on. So that's very important because the sample return investigations is really the graal of planetary science. First, you have the flyby mission, you have the orbital mission. You can land on the surface, but if you bring back something, that's really the best. Because then you can really understand the properties of the surface. And if you want to study life, for example, if you bring back sample from Mars, then it's better to study that with the powerful equipment on the Earth. So sample return is very, very good area of collaboration. Here it's a plot that I got from Anna. Also, they are working on to know more about the ice giant moon, like properties of the surface, hydrates, and also what happened in the high pressure state for the ice. And as you have seen, the icy moons are the most interesting target now of planetary exploration. So to know more about the ice and in high pressure system, because you have most of the moon, they are made of ice, so it's very important to understand that. And you can study that in synchrotron facilities. So that's also a very interesting area of collaboration. Another one is also there were some sample return of dust particles trapped in aerogel and bring back to the Earth. And here again, with synchrotron, you can study that in a non-disruptive way because the grains, they were trapped in aerogel, so they already suffered from this process. So if you study that with synchrotron, you don't need to disturb them again. So that's also interesting techniques for this kind of sample particles. So that's just a few examples. There are many, many, many. And here I was thinking just to fit some discussion that we've had with Angelica and colleagues, and maybe I'm sure we'll have in the future. So there are different areas of collaboration. You have also instrument testing and calibration, because I mean we need also to send instruments to space that are sensitive to X-ray, and some they work also in to measure X-rays. So you can test, you can calibrate. The sample return I mentioned. So Mars, we have a sample return of Mars, which is in the pipeline with NASA. I think it will take a few more years, but this is in the planning. And Mars being one of the most interesting targets for astrobiology, it's very important to bring back samples. So I think it will take maybe 10 more years. We are working with the Japanese colleagues to have a sample of the Phobos moon. and here maybe in the 30th. So in less than 10 years, we should have in principle samples of one of the moon of Mars, which is interesting because we think there is also particles of Mars at the surface of Phobos. So if you bring back samples from Phobos, you bring back something from Mars as well. Asteroid and dust. So the sample return is really something very important. As I highlighted for Titan, you study also planetary atmospheric chemistry, but also chemical reactions, plasma physics in the atmosphere, also um, uh, to measure the key reaction rates into the atmosphere. And for the people doing modeling of atmospheric chemistry, it's very important. Study of ice and dust, very important as well, in particular for the icy moons. Planetary interiors, you can get some information on the Earth's interior from your analysis. And now we are more and more studying other planetary interiors, like the giant planet, but also the moons around the giant planet, Mars, Venus, and space weather. I did not mention, but there is also a lot of space weather and plasma activities. And some ideas to collaborate was I think the sample return, I think, is the most obvious domain of collaborations. We discussed to have maybe some workshops. I have seen some in the past, some workshop, but not so much between the scientific community involved in planetary science and synchrotron facilities. So that's something we discussed a little bit this morning. But that could be interesting to mix the different communities and to have more people involved in this kind of activities. We have also, when we launch a mission like JUICE or other mission like Envision to Venus, we always have a guest investigator programs. So it's to allow people who are not necessarily involved in those missions to be involved. And they can propose lab experiment, ground-based observations, modeling, something which is not necessarily covered in our mission. And people say, okay, I would like to be part of your project, and they apply, and that could be also a topic. Advertise calls for beam time to community which do not know what you are doing and how to apply, and then some exchange program, also student, PhD, whatever. So a lot of ideas that we will explore in the future. But thank you for this visit, and happy to discuss any questions or to collaborate in the future. I will stop here. Okay.
Okay, so thank you very much, Olivier, for this very complete and detailed